Uh, okay, so I'll kind of like start by just explaining what the situation was yesterday of what we were trying to find. So let me share first like my GeoGebra. Um, so again, kind of like the idea here is that for example, let's say you have these 3 points. You could think of them as corresponding to some data that you measured, right? And you're trying to find a polynomial that fits the data. In this case, fitting the data doesn't mean that it will pass through all of the points, but kind of like it will be relatively close to the points that you were given. So because I'm going to show you pictures for this entire problem. That's why I have so few because otherwise like the visualization collapses. So let's decide again. I'll decide that I wanted to find a line that fits this data. Okay, so I'll try to use a line kind of like is as close as possible to these 3 points. So let me go back to the iPad. So what is going to happen is that you will let me see if I can go back to the iPad. Let's see if this works. Okay, so in this case, if you had those 3 points, yeah. So let me draw the points here. So this is what we were doing last time. So the points were X and Y. So one point was -2, 3. The other point is 1, -1. And the other point is 3, 2. Let's say 3, 2 is here. So this is 3, this is 1. And -2. And again, theoretically, I'm going to say, okay, I want to try to find a line that passes through these points. Let me try to do like a random line, right? A line is a polynomial of degree 1. That's how I'm thinking about it right now. So the way I'm describing it, it requires to like two numbers to be specified, like the constant coefficient and the coefficient in front of x. Okay, and then the idea is that again, because they're not supposed to like pass directly through all these points, what you want to minimize, because of what we were saying yesterday, what you would want to minimize, like in theory, would be kind of like the size of this error, right, which I'm putting in green. It's just that for practical purposes, it is easier to work with the error squared, right? So what we were trying to minimize, so you're trying to try to choose Z0, Z1, so that the error, like the error squared, which would have been the sum from I equals 0 to 2 of yi minus C0 plus C1 xi squared is as small as possible. But like the reason why I chose like these numbers is so that we can kind of like write it down more explicitly. So if you expand all of this out, uh, like this would be what? The first y value is 3, so it would be 3 minus C0 plus C1 x1, so minus 2 C1 squared plus the next y value is -1, so it would be -1 minus C0 minus C1 squared, and the next value would be 2 for y, so it would be 2 minus C0 plus 3c1 squared. Okay. So that is kind of like the squares of the errors like added together. The sum of the squares of the errors. I'm kind of like putting all the numbers in so that you see that literally this expression only depends on C0 and C1, right? Because you're pretending that you have the data, so like you do know the values for x0 for the points, and so like like the only unknowns would be kind of like the parameters of the polynomial. Is that making sense? So far, so good. So this is kind of like what you're trying to make small. So this is what you want to make small. So far, so good. Any questions up to this point? Okay, now again, for example, if you kind of like use different variables, this is literally a function that you studied in Calc 3, right? If you call C0 like x and C1 y, it is a function of two variables, right? So one way to like approach the problem is literally as a Calc 3 problem. So you have a function of two variables in this case. How do you find the minimum? Like you find the partial derivatives with respect to each variable and set them equal to 0. That's one possibility, um, which is totally fine. And you can kind of like do like a similar thing, like in complete generality for a polynomial of any degree and any number of points. So it just becomes like a kind of like a computation in taking partial derivatives. And that's all nice, but I'm going trying to explain it in a way that's a little bit more geometric so that there's kind of like a more clear picture in mind. So to kind of like find that picture, what you have to do is introduce a little bit of terminology so that you can apply linear algebra. So in this case, what I'll create like a couple of vectors and I'll create a matrix. So the first vector that I will create is a vector y, which just represents the values for the measurements, the y values of the measurements. So in this case, the y values are 3, -1, and 2. Okay. I'll also create a vector that keeps track of the coefficients that I need to find. So I'll call that vector C. So this would be just the vector C0 and C1. Okay. And kind of like the more important one, um, the crucial one is like the matrix. So there's also a matrix involved here secretly. And the matrix, the way I told you last time, you can find it, you know, kind of like the way the notation I wrote it was like this. Those are like the entries of the matrix. But what that means is kind of like more concretely is you take each of the x values of the points. So in this case, there are 3 points, right? Since there are 3 points, you take the x values and you start raising them up to the power of the polynomial. So the polynomial is, because it's a line, is power 1, degree 1. So you will raise them from 0 to 1. So you start by raising each of these numbers to 0, and then you increase each of these, raise each of these numbers to 1. And if it had been like a parabola, then you would have like another column where you raise each of these numbers to to the power 2. And if it had been a cubic, an extra column, so that is to the power 3. So in this case, because like like anything to the 0 power is just kind of like set up equal to 1, so you get 1 1 1. And then you get here in this case like the values for x, so you get -2, 1, and 3. Okay, so that is what the matrix is. So in this case, it's a 3 by 2 matrix, right? So far, so good up to this point. And okay, and so what I was then this is where we ended up yesterday. So what I was explaining is that all these sum of squares, like this sum of like the squares can be rewritten in like a matrix notation, which is nicer. So this is the same as, I mean, you can double check it, but we kind of like went through like details yesterday, but that is the same as y minus a times, oh, so sorry, I used y in red. Okay, so basically, you subtract a times c from y as vectors, right? Because again, like, this is 3 by 2, and the vector is 2 by 1, so you can multiply these two out, and then you get a 3 by 1 vector. So you can, and this is 3 by 1. So you can subtract these two vectors, and the length square of that vector is what this thing corresponds to, like the thing that we're trying to minimize. So what we're trying to make small is kind of like what we're trying to make small is the length square of the difference between y and the vector AC. So we are trying to make this like a small vector. Uh, so we're trying to make the length of this vector small. I mean, like the length square, but if the length is small, then length square is also small. Like that is not such a big thing. Just to make. So what I thought I would do is kind of like show you some pictures so that you see how it all looks like in this case. So for example, in this case, the matrix A was 1, 1, 1, -2, 1, 3, and the vector C is C0, C1. So if you do if you do A times C, right? If you multiply them out, what do you get in this case? You get C0 minus 2C1, right? And then you get C0 plus C1, and then you get C1, C0 plus 3C1, right? So those are the entries of the vector A times C, right? So what I'm going to show you is kind of like what I'm going to show you is kind of like how this looks like in 3 dimensions, because this vector has 3 entries, right? So because the vector has 3 entries, then you can show it, like you can plot it on R3. So that's what I'm going to proceed to do now. Okay. Let me stop sharing my screen because now I have my iPad, because now I have to go to GeoGebra. Okay, let's see. So okay, so what I'm going to show you first are the columns of the matrix A. So A was a matrix with 2 columns, right? I don't know if you can be checking your notes while I do this, but if you notice, like the matrix A, the first column of the matrix A was 1, 1, 1. Okay. So this is the vector 1, 1, 1. Okay. This vector that you see hopefully here in green. So this is one of the columns of the matrix, and the other column vector was -2, 1, 3. So there it is. Okay, so those are the 2 columns of the matrix represented as, in 3 dimensions, because they have 3 entries. Okay, now if you do the matrix multiplication A times C, right? If you do the matrix multiplication A times C, you will get a new vector. Oh, actually, here it is. Okay, you will get a new vector, which is like the one I'm representing in blue. This is like the one that I wrote, is C0 minus 2C1, C0 plus C1, C0 plus 3C1. I don't know if you can see my pointer, but this is exactly this vector. It's just that on GeoGebra, I had to call the parameters A and B instead of C0, C1. But if you notice, like the entries of this vector, there are the ones that I wrote earlier. But kind of like the point is that depending on the values for Z0 and Z1, you get different, like the vector will look differently, right? Because that's what you're trying to determine. You're trying to determine the values for Z0 and C1. So if you give different values to Z0 and C1, the vector will look different, okay? The idea is that no matter which values you give, right? No matter which values you give, the vector is a linear combination of the columns of the matrix, because that's how the matrix multiplication works. That's what we talked about yesterday, that if you multiply a matrix by a vector, the answer is like a linear combination of the columns. So in fact, this vector always lives in the plane generated by the two columns of the matrix. So when you have two vectors, you can kind of find a plane that passes through them in 3 dimensions. So I don't know if you can see it here. Maybe this makes the picture more clear, right? Because if you can notice, hopefully, you can kind of like see that no matter how I'm drawing the vector, it always kind of lies on the plane. Is that kind of clear from the picture that it's always on the plane? So no matter which values for Z0 and C1 I use, no matter which values for them I use, like the vector is always on the plane. And this plane is usually called the column space of the matrix, although you don't need to use that terminology if you don't, maybe if you haven't taken like linear algebra in a long time, or you haven't just taken it at all. The point is that, when you multiply them, when you do the matrix multiplication, the vector that you get is a combination of the columns of A. Okay? So, okay, so this is the setup so far. The other vector that's important to keep an eye on is this vector with the y values. So if you remember the vector of the y values, what were the entries for the vector with y values? It was 3, -1, 2. So this is a vector with the y values. Which can you let me see if I can delete the axis, because I think it's kind of makes it more confusing. Okay, let me see if I can erase the axis from the picture. Okay, yeah, I think that looks better. Hopefully it does. Let me see, because otherwise there are too many like things going around in the picture. So let me kind of like make this a little bit darker, the plane. So that you can see it more nicely. Okay, I think this looks good. Okay, so the red vector represents the y values. And so kind of like hopefully the thing that's pops out when you see this picture is that the red vector is not on the plane, right? The red vector is not on the plane generated by the columns. And that is why what kind of like the meaning of that is that you cannot find a line that passes through all the points exactly, actually. That is what it translates to. So the fact that the vector is not on the plane means that the best you can do is an approximation, because there won't be a line that passes through all these points. That's kind of like the geometric interpretation of solving a system of linear equations. So the next best thing, right? And this is what we're trying to do. So there is a vector kind of like that measures the difference between the blue and the red vector, which is this y minus a times c vector, which is in purple here. Okay, so what you're trying to do is kind of find the values you are trying to determine the blue vector. You're trying to find the values for the blue vector that will make the purple one as small as possible. Because again, the red one is completely fixed. You cannot change the red vector. But if you start changing the blue vector, you see that if you give different values to the blue vector, you see that the purple one changes in size, right? So the purple one is kind of like the error, okay? That is the error vector that we talked about yesterday. So basically what you want to do is like this purple vector as small as possible. That's kind of like the idea. You want to minimize the length of this purple vector, okay? Because hopefully you can see here, like if I start giving, I think it's kind of clear from the animation. If you choose different blue vectors, the purple vector has different lengths, right? So you're trying to find the vector, you're trying to find the vector that gives you a purple vector with the smallest length. Is that making sense? Kind of? So far, so good. And the idea, and this is what people call like a vector projection, by the way. So if maybe that rings a bell. So kind of what you actually try to do to solve this problem is to make the purple vector perpendicular to the plane. So you're trying to make it into a normal vector to the plane. So the game becomes, can you choose the values for Z0 and Z1 so that the purple vector ends up being completely perpendicular to it. So in this case, you can, let me see, and it will be something like this. So hopefully you kind of see here that there's kind of like let's just hide the green vectors for a moment. Hopefully you can see here that there's kind of like a right triangle made out of like the purple vector, the red one, and the blue one. And that is kind of like the solution to the problem, because the purple, when it is a right triangle, that is when the length of the purple vector will be minimized. That is what doing a vector projection means. So I'm not going through, I'm not going to justify that part, but hopefully the picture kind of like makes it plausible that that's how it should work. So kind of what I'm trying to say is that the goal is that you're trying to find the values for z0 and z1 that would make, you're trying to find the values for z0 and z1 that would make the vector, the purple vector, perpendicular to the plane. Okay? Is that making sense? And that's called like a vector projection. I'm about to draw the picture on the iPad now, but I did want to show you the animation first because I think it's kind of like useful to see what's going on, like makes it more transparent. So let me write that down. Let me stop sharing, and then let me write that down here. Okay, so kind of like the picture to have in mind. So here's the picture that explains the problem. So the picture is that you have a plane. Let me see if I can make it a little bit better. You have a plane. Let me color it. Okay, so let me see if I can use the same colors as in GeoGebra. So on this plane lives the column vector of the matrix. So the first column vector of A, I'll call it column 1. Here also lives the column vector, the second column vector of the matrix. And then the vector A times C is a linear combination of those two. So this is what A times C represents. It's a vector that lives on the plane. And the idea is that if the vector y is somewhere in here, what you want is, this is the vector y minus 8 times c. That's what the purple vector represents. And so kind of like what you want is the length of that vector to be as small as possible, and that happens precisely when the purple vector is perpendicular to the plane. So you want this length. Or this vector to have a minimal length. You want this vector. And the idea is that happens precisely when the purple vector is perpendicular to the plane. So this occurs when y minus 8 times c, which is what we had called the error vector. So this is like the name for the error vector. It was basically that. So the error vector has to be orthogonal to the plane. That's kind of like the criteria. Um, okay. So when is a vector, what does it mean for a vector to be perpendicular to a plane? Um, well, it means that it is perpendicular to every, that it has to be perpendicular to every vector on the plane, okay? But every vector on this plane is a combination of the columns of the matrix. So basically, what you need essentially is for the vector, the error vector, to be perpendicular to every column of the matrix of A. So what you need, in fact, it's easier. In fact, what you need is for E, for the vector E, to be perpendicular to each column of the matrix A. So in this case, because there are two columns, right? In this case, because there are two columns, you would write this as how can you check two vectors to be perpendicular? Their dot product has to be 0, right? Like if you remember the dot product. So what you need is that the dot product between the column vectors and E is 0. So you need the first column vector dot E would be 0. And you also need and you would also need the dot product between the second column and the vector E to be 0. That's what it would tell you that the vectors are perpendicular. Is that making sense? So far, so good. But here comes like even the more interesting part, and this is why I started yesterday talking about how do you interpret the multiplication between a matrix and a vector, because let me just go back to yesterday's notes. This is literally what I wrote at the beginning of last class. So you see, like you are trying, you need you need a few dot products to be 0, right? And one of the things that I said yesterday is that you can think of the matrix multiplication between the multiplication between a matrix as a vector as a bunch of dot products between the rows of the matrix and the vector v, right? So we're almost there because here I have the vector e, right? I have the vector e here, but like I said that we had to use the columns, right? We had to use the columns, not the rows. So is there an operation that you remember that turns the rows of a matrix into the columns or vice versa, the columns into the rows? Maybe just to rephrase it. Is there a way, what turns the rows or what turns the columns of of a matrix into the rows of another matrix? Maybe if I phrase it that way, it makes more sense. What would you do to the matrix? You transpose that, yes, exactly. So what that means is that a more elegant way of writing the equation is just saying that A transpose times the error vector should be the 0 vector. So exactly. So this is the same as A transpose dot E equals 0. Because again, multiplying a matrix by a vector multiplying a matrix by a vector is doing the dot product between the rows and the vector, but the rows of the transpose are the columns of A. So that's kind of like how it works. Okay, and if you work this out, we're almost at the end, actually. If you work this out, what is E? The vector E was Y minus A times C. So this needs to be the zero vector. Okay, so that gives you that A transpose, how do you do a multiplication? You can distribute. So that gives you that A transpose Y minus A transpose AC should be equal to the zero vector. Okay. So if you just move like the second term to the right side, that tells you that, so this means that the vector C should satisfy that A transpose Y equals A transpose A times C. It's usually written the other way around, like, exchanging the sides just so that the variables are on the left side, because like that's a common way of writing an equation. So just move the terms around. And this second version of writing it, that is what's called the normal equations for for the polynomial least squares method. So these are called the normal equations. And this is what you have to solve in general. So if you want to find the coefficients that gives you the polynomial, you solve these equations. So these are called the normal equations. Is that making sense? I'll do an example. I'll do now like a few examples, but that is kind of like that is kind of like the end result of like all this discussion. To find the coefficients of the polynomial, you have to solve that equation for the coefficients. Like this is the equation that the coefficients must satisfy. This is the same equation that you would find if you set it up as a Calc 3 problem, where you take all the derivatives with respect to all the partial derivatives with respect to zero. And so these are like the equations for the critical point in a sense, like, but I'll give a couple of examples in a moment to kind of make it more concrete. Let's do like a 5-minute break, just because this is kind of like the end of the theoretical part for today's class. So like then like we can just start talking about the examples. But also that way, if someone wants to ask me something about like this derivation, they can. But if not, yeah, let's say 11:10, and then I'll show you a bunch of examples like of how this looks like. But if you want to ask me something about this, feel free to do so. I'll stop the recording just in case. Okay, so before I do the examples, let me see if I can share this quickly. Let's see. Okay, so so I did update yesterday the practice problem. So I will kind of like after the class, I'll send like an announcement. with some recommendations. First, we don't, since I said like I canceled today's quiz, so like the next quiz will be on Monday. So I'll send the like the recommended problems for the Monday's quiz, and also I'll send you like the problems for you to work on for like the assignment. Like the assignment, the next assignment, the next. It was originally for this Saturday, but I think it makes more sense just to push it for a week so that there's more things that I can include there. So I'll do that after we're done with the class. And then someone had also asked me about like, how do you choose in general um, the degree of the polynomial when you're trying to do this least squares method? Because if you remember what I was saying yesterday is that you kind of have to decide ahead of time which polynomial you want to use, right? So you have to decide, am I going to use a cubic or a parabola or something of degree 10 or whatever? Once you have made that decision, then you can try to solve the least squares problem, like which in this case now, because of what we just said, would be the normal equations. But of course, it's kind of like an interesting question, like, how do you what are the clues to try to decide the polynomial that you should use, like in the sense of the degree that you should use? So the thing is like that does get more into statistics. I was trying to find yesterday whether there was like a useful YouTube video that would explain it in a couple of minutes, but that is wasn't I couldn't find any good reference for that. So there is a book that is pretty good. Um, I have it here. And which actually like I have been using a little bit for like some of the topics for the class. So I posted a chapter of the book here in extra readings because in fact you can kind of like access any chapter of the book through Rutgers libraries online because it's from Cambridge, and with the Cambridge books we can kind of like download for free the textbook, at least if you are okay downloading the individual chapters. So I posted on Canvas a chapter that's relevant. If anyone is curious, like you don't have to read it. It's a little bit of like a lot of information, but if at least I can pinpoint you to where you should go. So yeah, like because this chapter even discusses like branch interpolation. It discusses like all the interpolation things that we have been talking about. But if you go to around, where is this? Where are you? Like, if you go closer towards the end of the chapter, okay, this is where it starts talking about the least squares. First, I was going to do this, but then I was okay. Maybe there's not enough time for that. Like, it also discussed like how do you incorporate if you know the uncertainties in your measurements, how do you incorporate that into the problem? So it has like a nice discussion of that, which you can check if you're interested. But then like more to the question about like choosing the degree, if you go here, where is it? As I said, it's like and also nice thing about this book is that it has like the Python code for certain things if you want to kind of like try them for yourself. Let's see. Wait. No, it's before this. Oh, okay. No, 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 no. Oh, here it is. I think so. Oh, right, right, right. Like so. Actually, let me find the page. Like I have it here, right? Oh, it's section 6.5. No. Oh, okay, it's in 6.6. Sorry about that. So where's 6.6? Oh, okay. This version that I have is a little bit different. That's what it explains it. So maybe it is somewhere else. Huh, that's interesting. But okay, because apparently the maybe oh, this is the second edition. So maybe I'll see if I can find the second edition chapter because like I think I may have posted the first edition version. But the second edition does have like kind of like a section that discusses like, like it does requires like some statistical knowledge to like, how do you fit that, how do you find that degree? So it has like a nice conversation about that. So I will see if I find that if I'm able to find chapter 6, but for the second edition of the book, because then it does have like a nice section that go over that. Probably it is also somewhere in here, but explained in a slightly different way. But regardless, this is like a useful chapter if you want to go into more detail, because it does discuss certain things, about like statistical, like the variance and like certain things like that I'm not going to tell you about, because that would require like knowledge of probability theory. So so if someone wants to know like, like those things, like this is like a good source to check, regardless of like this thing about like the degree of the polynomial. So I just wanted to say that in case like someone wanted to like, kind of like learn more about that. But now let me move to the examples. So let me summarize what the goal is. So like this is like the method, okay? So here's like the algorithm that we have. So let me summarize everything that we have done. So kind of like the input data is that you have n number of points. Okay, that is what you start with, and also you can consider this as as part of the input, the degree of the polynomial that you're going to try to find. Okay, so let's also put that into the degree of the polynomial. Okay, and then the idea is that the goal is to find, right, like what you're trying to find is the coefficients of the polynomial. So you find like what the output is going to be is the coefficients of the polynomial. Which minimize the error squared, right? Like I won't write the formula again because like, I'll just write it like this. Okay. And all the thing that we have done so far is just to say that to find the coefficients, you arrange them into a vector, right? So what is the solution like? So the solution is you turn the coefficients into a vector. So you construct the the vector of coefficients. You also construct the vector of y values. And you also construct the matrix of the different powers of the x values. So the matrix xi to the j, which again, that is going to be 1, 1, 1, 1, 1, then x0, x0 square, x0 squared, x0 cubed, up to x0 to the n, then x1, x1 squared, x1 cubed, up to x1 to the n. So basically you just, on each row, you just take all the different powers of each x value until you hit the degree of the polynomial. And then you would go up to x2, x2 squared, x2 cubed, up to x2 to the n. And you go like that, until you get to the last point, which would be xn minus 1, xn minus 1 squared, up to xn minus 1 to the n. So this is going to be a matrix. So how many rows does it have? It has as many rows as points that you had. So it has n rows. So this is like an n by n plus 1 matrix. Because how many exponents are there? How many columns are there? Zero column, you know, kind of like, you know, there are n columns here plus 1, which is like the degree 0. So this is like an n times n plus 1 matrix. And you just have to be careful with, because the n is being used in two different ways. And the idea is that the vector c solves the normal equations. So and so what I'm going to do now is kind of like put some examples so you can see more concretely how this looks like, because that gives you some intuition about, like, you know, what happens in general when you're trying to solve these equations. Is that making sense, like the notation and everything? Or let's say, write it like C is the solution to. Okay, so first example, the 3 points that we were talking about. So example 1, with the 3 points that it gave you. So this is like the previous example. I had 3 points, right? So my n, big N, in this case is 3 because that's the number of points, right? I have 3 points, and I had chosen a degree 1 polynomial, right? Because I wanted to find a line, right? So I wanted to try to find a line. So under this notation, you construct the vector of y values. The vector of y values, we had already talked about this. It was 3, -1, 2. The coefficient vector is C0, C1, because a degree 1 polynomial only has 2 coefficients. And the matrix A, we also talked about it. The matrix A is always 1, 1, 1, and then x0, x1, x2. You know, there are no more higher powers because it's degree 1. So in this case, it was 1, 1, 1, -2, 1, 3. Okay. So how do the normal equations look like in this case? So the normal equations are, again, they are A transpose A, C equals A transpose Y. Okay, what is A transpose? Again, A transpose just like flips the rows with the columns, so you change the rows. So the first column becomes the first row, so it becomes 1, 1, 1, -2, 1, 3 times 1, 1, 1. Sorry, I think something happened to like my internet connection because I got unplugged. Can you give me just 2 minutes, because I do want to double check that I didn't miss that the recording didn't disappear. So I'll just kind of like close off the session for me, but like, you know, I will kind of like come back in 3 minutes. I just want to make sure that like the video wasn't lost, if that's okay. So like just give me like 3 minutes if that's okay, and I'll be right back. But I'll log out just to make sure like that the video does save. I'll be right back.